Hey everyone, welcome into this lecture video on inverse hyperbolic functions. In this video we are going to derive a formula for the inverse function of the Cinch function. So remember, if we have y equals sinh of x, then what must the inverse function be? Well, this must be a one-to-one relationship, right? So y equals sinh of x if and only if x is equal to arc sinh or inverse sinh of y. So you can write it as sinh inverse, or you can write it as arc cinch. So like I said, I'm going to derive the formulas for arc cinch. By the way, now we're going to write this formula. This function is like f of x equals arc cinch of x. Usual deal here, right? Where we use the x and y, you swap the positions of the x and y to define the function, but then the function is usually in terms of x. So we want to try to write a formula, or derive a formula for arc cinch of x, and at that point I will then write down the formulas for a couple other hyperbolic inverse functions, but I want you guys to derive those on your own. So it's very important that you're able to do this derivation on your own. So let's start. The first step is to write down the formula for sinh of x, right? So just write down y equals sinh of x, but remember that we have a formula for this. This is 1/2 e to the x minus e to the minus x. All right, the next step, if we're going to try to find the inverse function, is to swap the roles of the x and the y. All right, so the next step is to write down that x equals 1/2 e to the y minus e to the minus y. And at this point, we have to try to solve for y somehow, some way, right? So this is our goal, to try to solve for y. And the first thing we notice is that we should be able to multiply across by 2. So if we multiply through by 2, we get 2x equals e to the y minus e to the minus y. And now I'm going to get everything on the same side of the equation. All right, so I'm kind of drawing these arrows. This is just showing us our steps, right? So the next step is if I subtract the 2x over, then this can be written as e to the y minus 2x minus e to the minus y equals 0. All right, and at this point, this is a little weird, right? How are we going to solve for y? It's not so clear. So what I want to do is I want to multiply this entire equation by another copy of e to the y. And when I do this, you have to ask yourself, is this allowed, right? So am I allowed to do this? So our goal is to find the solution of the equation, to find the y that solves this equation. And just remember, though, that e to the y can never be 0, right? E to the y is always positive. And so multiplying this through is not going to change the solution of the equation, even though it's going to change the way that it looks. And this e to the y is going to go to all the terms, including this term on the right-hand side. It turns out it's just going to be 0, right? But in our mind, we have to remember that this 0 is here. And so when we distribute this out, we end up with e to the y quantity squared minus 2x, which I'm going to put in parentheses, times e to the y, minus e to the y times e to the minus y is just 1. Right? It becomes e to the 0. You add the exponents, you get e to the 0, that's 1. And at this point, we want to try to solve this for e to the y. All right, so that's just multiplying through. Our goal now is try to solve for e to the y. And here we notice that the e to the y term, if we just make a little replacement here, if you make a little swap and you call this like a u or something, I'm not even going to do it, but if you were to do it, this would just be a quadratic equation. So u squared minus something times u minus 1 equals 0. That's a quadratic equation. And quadratic equations can always be solved by completing the square. So I'm going to leave it as e to the y here, but that's the idea, right? So we're going to solve this for e to the y as a quadratic equation. So there's our minus 2x e to the y. Now I'm going to leave some space, and I'm going to move the 1 to the other side. So just add 1 to both sides. And then to complete the square, what do we have to do? We've just reviewed this recently, right? So what do we have to do? We have to add 1/2 of the coefficient on the first power term, the linear term. So half of this coefficient is a minus x, but then quantity squared, right? So this is then minus x quantity squared. But minus x quantity squared is just x squared, right? So before I do the factoring, I'm going to write this out one more time. It's e to the y squared minus 2x e to the y. This then becomes plus x squared, right? Which we're not going to have to worry about that, but over here it's going to matter. So this becomes 1 plus x squared. And now on this side, this is a perfect square. That's the whole point. We completed the square so that this is now e to the y minus x quantity squared. right? And that then equals, you can, sometimes you'll see this written with the x squared first, so I'm gonna rearrange it. Changing the order doesn't change anything, right? And at this point, we want to solve for e to the y, right? So we have to take a square root. So when we do that, we end up with a plus or minus on this side, right? Because you get an absolute value on the left-hand side. So this leaves us then with e to the y is equal to x plus or minus. So I did two steps here, but plus or minus the square root of x squared plus 1. And now you have to ask yourself, which of these signs is the correct one, right? Should it be plus or should it be minus? In our inverse function, there should only be one inverse function, right? Remember the graph of Cinch. The graph of Cinch. So if you're doing Cosh, you have to make a restriction before you start. But the graph of Cinch looks kind of like this, right? This is y equals Cinch of x. This is a one-to-one function. It's a bijection, right? It's got it is one-to-one, and its domain is all real numbers, so it's got an inverse function for all x, right? An inverse function for all x and all y. So what should it be, right? Well, e to the y, we've just said previously that this number has to be positive, and when you compare x with x squared plus 1 square root, the square root of x squared plus 1 is always larger than x, right? Even if x is positive, this is always going to be larger, right? And so that means that we have to take the plus here. Otherwise, we would get a negative answer, and e to the y. So the reasoning here is that e to the y is always positive, right? And so to get that, we need to keep that plus sign. And so now what we end up with is that the exponential of our inverse function, e to the y, remember we're looking for y, right? E to the y is equal to x plus the square root x squared plus 1. And at this point now, this right-hand side is always positive because we made it that way. We made that choice, right? So we can take the natural log of both sides. And what we end up with is, and we don't even have to worry about absolute values with our natural log because of everything's positive here, right? And what we end up with is that our inverse function, y, which again is the arc Cinch function of x, the formula for this is that this is the natural log of x plus the square root x squared plus 1. All right? And so that was carefully worked out, but there's a formula for the inverse function of Cinch. Remember, you can write this as Cinch inverse of x if you wish. All right, now, like I said at the beginning of this video, you have to be able to compute two other ones. By the way, the domain of this is that x is allowed to be any real number. All right? So there are two other inverse functions that you have to be able to compute. So you must be able to derive, I should say. You must be able to derive these formulas. They go exactly the same way, where you start with the definition, you swap the x and y, and you solve for y. And you just very carefully work through this calculation. It'll be very similar. You have to make some choices at certain points, and you have to think about the graph of each one, right? So we did Cinch together. The other two that you absolutely have to know how to derive are Cosh inverse of x, which I'll write sometimes as arc Cosh of x. This one's very similar to the one that we just did. It's the natural log of x plus the square root of x squared minus 1. All right, so that's different. So that's different. And then that shows you how the domain's got to be restricted, right? So this x has to be greater than or equal to 1. So there's the domain of the arc Cosh function. By the way, think about this. I'm not going to work this out in this video, but think about, is this a correct restriction? Think about the graph of Cosh and how the y values of Cosh behave, and then ask yourself if x greater than or equal to 1 makes sense for the inverse function. And then the last one that you have to be able to derive is the inverse Tange, or the arc Tange of x. And this one, turns out, it can be written a couple different, you can see lots of different ways to write this one, because this one is they're all defined by logs, right? But this one's got a log with some fractions. So this is natural log, 1/2 natural log of 1 plus x divided by 1 minus x. You can switch the orders of these. You can make a square root in there with this 1/2. You can go in and become a square root, which might come out in the computation. But we know that log is not defined as 0. It's also, obviously, if you can't divide by 0. So this tangent has to be defined between -1 and 1. And if you look at the graph of tangent itself, so that's arc tangent, that's defined between -1 and 1. If you look at the graph of tangent itself, this will hopefully make perfect sense to you. So make sure you can derive these two formulas as well as being able to derive the one that we just did together. And we'll leave this video here, but we're going to use these functions moving forward.